Good afternoon, everybody. I guess I should thank the organizers first for inviting me to an applied math symposium. I must say I rarely get invited to math workshops, so I've been enjoying especially today's session very much, and I hope to tell you a little bit about the work that I do. This title here may not make sense much to you just yet. I'm going to explain everything except Hartree-Fock. So if you don't know what Hartree-Fock means, it's just a fancy mean field method we do in electronic structure theory. We have one equation that we care, and this is the only equation we really try to solve approximately. This is Schrödinger's equation, and the challenge comes from, as we heard from previous lectures, the fact that Hamiltonian here has an exponentially large dimension. The specific Hamiltonian we have is just interacting Coulombic particles. So every electron and every nuclei in these molecules, if you give me their charges and location of them, I can easily convert them into this Hamiltonian here. And this Hamiltonian, we can discretize it in grid or discretize in molecular orbitals of your choice, or discretize them in any other basis that you would like to work with. Exact solution is naturally an exponentially large tensor. So let's say we discretize this wave function object here over some grid points. Each of the electron will get some entries. So I'm going to assign m grid points for each of the electrons. And representing this n electron wave function takes m to the nth entries. So we don't really want to even thinking about storing this exact solution, even if we could compute them.
So is there a reason are you including electrons and nuclei, or what are you including here?
It depends on where you're coming from, but you can think of it as entire, every particle in the system.
Okay.
Yep. It doesn't really, It could be electronic wave function if you're a quantum chemist. It could be every degrees of freedom in your system if you're not a quantum chemist, I would say.
But includes ions too, yeah.
You could include the ions too. The exponential bottleneck doesn't go away. It gets only harder. So time to the exact solution is, of course, exponential scaling. And quantum chemistry is really all about making new approximations to avoid running into any of these exponential scaling, either in storage or the computational cost to the approximate solution. There are some challenges in electron correlation. I think Nick Mayhole really summarized very well. I'm going to briefly go through my own view on the current challenges we have to solve in our field. Electron correlation is everything beyond Hartree-Fock theory, so everything beyond mean field theory. So this is really everything we do in quantum chemistry. So this has some similarity to what Nick showed in the previous lecture. This is a molecular magnet and oxygen revolving complex, some model of it. I shamelessly took these figures from my own paper, but a lot of people study these in quantum chemistry. And why are they interesting from quantum chemistry point of view? Well, the first thing to consider is static or strong correlation. I'm going to tell you what this actually means by. It means that there is strong spin or it could be actually both spin and charge, but there is a fluctuation that is so large that it really makes it difficult to assign either oxidation numbers, meaning the local charge states of these individual metal centers, or spin states of these metal centers. So strong spin and charge fluctuation is the really signature of what we mean by strong correlation. And you can't describe them by Hartree-Fock theory. And this usually happens primarily in balanced space. So Nick actually covered what we mean by active space in this context. So I'm going to skip that part. But you can actually think about some reduced space in these gigantic molecules that sort of contains the essence of this static or strong correlation. And we do end up using a lot of brute force methods. I haven't seen a successful method to handle static correlation that doesn't scale exponentially with the number of degrees of freedom, including Nick's method. This is where we are in terms of static correlation. Then there is potentially a bigger elephant in the room, which is the dynamic and weak correlation. This is the correlation that is not contained in this valence active space we identify for strong correlation. There are many slightly filled orbitals to consider. And to give you some sense for this one had 3,000 orbitals to solve when I studied this. And this one, with some well-truncated model, you can bring it down to 1,000 or 2,000 orbitals to consider. So this is where perturbation theory, assuming the static correlation is well handled, perturbation theory should own this type of correlation. Or if you want to be a little more sophisticated, you can do diagrammatic methods called couple cluster theory. And these are really the state-of-the-art treatment for dynamic or weak correlation. And I do have a modest wish list for a method that I would like to use myself as a quantum chemist, given these two types of electron correlation we have to think about. Strong correlation, I'm going to be fine with using brute force method. As I said, there have been no successful method that is generically applicable to any types of problems you have without scaling exponentially. Having said that, well, then we should be able to treat weak correlation almost perfectly. This is relatively easier to handle. Perturbation theory seems to be the right choice of method for weak correlation if strong correlation is nicely cleaned up by one of the brute force methods. So we do aim for 1 kcal/mole in relative energies, and this is where we can directly compare with experimental observations that you do see in your lab. So with just strong correlation, you can't really be quantitatively accurate. It's really actually the dynamic correlation or weak correlation that will bring you to the realm of directly comparing with the experiment. And I do want my method to scale polynomially out of active space. So as I said, overall, this method will be exponentially scaling because of the active space. But I'm going to actually focus more on having low polynomial scaling for out of active space. I want thousands of orbitals all being correlated beyond Hartree-Fock theory. And I do want my method to be size consistent and size extensive. It's a property that I'm not going to go into too much details, but if you have a method that is not size consistent or not size extensive and you talk to your quantum chemistry friends, they will all of a sudden turn around and try to think about some other method to use. So these are really the properties that we do value. So I want my methods to be size consistent and size extensive. And this modest goal, I'm not solving strong correlation here, I'm solving weak correlation on top of strong correlation. This is not yet solved. This is a modest goal. Question?
Sorry to interrupt. It's just, can you just shed some light on when you say spin charge fluctuation? Like, I know there is no very standard definition of what is strong correlation, but for example, in my case, like I just study the bond dissociation, and I don't deal with like what is spin involved, or I just deal with like closed shell systems. So in that case, all I can think about is when I have like a heavy electronic system, or maybe there are a few cases where, for example, BH2, the orbital interactions is like kind of weird, or it's like not like completely known to us. Then the electronic energy levels are like densely populated, and that's somewhere that is kind of one example of strong correlation. But in your case, like as you're saying, can you say like more about what is spin charge fluctuation that you're talking about, or?
I could try to go back to this example. So in this chromium-9 molecular magnet, each of them has 3 open shell electrons. And we do know from the experiment that the ground state is quartet ground state. So if you have 27 unpaired electrons, they have to be, almost everything has to be antiferromagnetically coupled down to the low spin manifold. So this is where the spin fluctuation comes from, because you can't actually assign single spin configuration for individual chromium atom. But the even more difficult case is to handle actually charge fluctuation, where this bridging fluorine atom actually takes away some electrons or donating some electrons to the chromium ions here. So, so with the charge fluctuation and spin fluctuation, all of them consider we don't really have a good method to handle this other than the brute force approach. Yeah, this paper is just about spin fluctuation. We do have a very nice method for handling spin fluctuation exactly with polynomial scaling. But with charge and spin fluctuation altogether, we don't really have a tractable way to do it. Does that make sense? Yeah. Let's see. Yep, so this modest goal is yet to be achieved, and this is what this talk is going to be about. Let's have a look at some bond breaking. So I'm going to artificially introduce spin fluctuations. So all these broken bonds with unpaired open shell electrons, they have to be antiferromagnetically coupled down to the singlet in this case. And this is really the hallmark of strong spin fluctuation. I'm going to take classic examples, H4 and nitrogen triple bond breaking. So here I'm going to fix these bond here, 1.23 angstrom, and I'm going to just stretch these blue bonds. That's the parameter I'm tuning, and the longer the bond distance, these open shell electrons will lose the charge transfer character completely. All methods I will show you use the same reference state called CAS-SCF. So there is a pretty good active space. You can identify 4 orbitals in this case, 6 orbitals in this case. I'm going to do brute force solve of them. CAS-SCF is affordable to do for this tiny system. I want to note the basis set size. We are not really doing minimal basis set. And all these acronyms you don't really need to know other than the last one, which contains AFQMC, which I will talk about later. With the weak correlation, of course, we should be using near complete basis set quality for these tiny molecules. And my goal is really to reach 1 kcal/mol accuracy. And depending on the choice of method, you probably have seen some of these methods. Some of them are very widely used, CAS-PT2, NAP-PT2. They all look pretty bad on this energy scale. And you can sort of see the variance in variation in energy is like 8 kcal/mol, and this is even like 25 kcal/mol. So this is by no means an easy problem to solve, even for state-of-the-art, we call multi-reference perturbation theory or multi-reference couple cluster theory. There's more than strong correlation to think about when your system has both weak and strong correlation. And I want to really emphasize these purple or pink data points here. They are within this dotted line, which is really the chemical accuracy across the bond distances we consider. And that is the method I'm going to talk about for the rest of this talk. I'm going to give you very brief history of AFQMC. It was developed initially for lattice field theory by great physicists in the 80s. And we've studied a lot of lattice Fermioni model in condensed matter physics. Most of the time people say QMC, they really do mean this BSS type quantum Monte Carlo, especially in condensed matter physics. And there was a paper by Shiwei Zhang in 2003 where he extended this BSS quantum Monte Carlo method for arbitrary Hamiltonian. The complex Hamiltonian we have in quantum chemistry can now be done by the same QMC method. In 2022, I teamed up with my friends at Google, and we thought about how to bring quantum information science into AFQMC as well. And I'm not the only one working on this. There are a bunch of people in my field and physics doing great work with AFQMC. AFQMC in quantum chemistry, since 2003, it's getting more and more popular. So I will give you some sense for where AFQMC actually fits into quantum chemistry toolbox. So here on the y-axis, I have accuracy. On the x-axis, I have cost. N is the system size. I can do mean field at the cost of n cubed, which is really considered to be the cheapest in this plot. I do have full CI here, and as I said, the wave function, the exact wave function, this is a brute force exact method, contains exponentially many entries, so it's not surprising that the cost of obtaining full CI solution is exponential in n. I have low-order perturbation theory called MP2. This is when you have a good mean field state and your problem doesn't have strong correlation. Maybe low-order perturbation theory will clean up all the mess and then give you good enough accuracy. And there is couple cluster theory, which is a diagrammatic method. These are CCSD parenthesis T and CCSD. And AFQMC fits right between MP2 and CCSD in terms of the cost, and its accuracy really rivals CCSD parenthesis T, which is the gold standard in our field. I just put these molecules to give you some sense for what you can do with these methods. So if you're close enough to MP2 and mean field, you can easily do C60. So there are 60 second row atoms, carbon atoms. But if you're insisting on exponential methods, brute force method, you can only do maybe 2 oxygen atoms with quality basis set. I've done with AFQMC some transition metal complex. So these are sort of a complicated electronic structure enough. This is called iron porphyrin. This said easily 2,000 orbitals total. So with the cost we are paying between MP2 and CCSD, 2,000 orbitals is not a big deal. We've done also recently, only very recently, you may wonder where this accuracy, the vertical value is coming from. It's coming from running lots of benchmark data we have in our field. So we've run more than 1,000 data points for AFQMC so that we can actually pinpoint where the accuracy should be put on in terms of empirical accuracy we know in the field. With that, I will explain what AFQMC is. So this is doing, the first thing you need to know is imaginary time evolution, and the QMC part will come later. This is the generic Hamiltonian we have, non-relativistic quantum chemistry Hamiltonian. I have one body and two body term. Imaginary time evolution, if you're from applied math background, this is really a power method. We're interested in computing the lowest eigenvalue of this Hamiltonian. So we're going to do power method by converting this, exponentiating this operator h, and then apply, take the limit of tau going to infinity. So when this tau minus infinity will give you exact ground state, which is psi naught. The only assumption we need is that our starting point, phi naught, has some overlap. It doesn't have to be even big, some overlap with psi naught, some finite overlap. That's the only assumption we need. And in the long tau limit, we will actually get the exact ground state, psi naught. You can sort of see why this should work by expanding phi naught in the eigenbasis of H, which is psi naught, psi 1, and etc. And because they are eigenstates, I can act and evaluate the eigenvalues when Hamiltonian acts on them. And then I can pull out the common denominators e to the minus tau e naught. And then you sort of see these exponential factors all carry some energy gap. They're all positive, multiplied by minus infinity. So you will immediately see as tau goes to infinity, all these terms, starting from psi 1 and psi 2 and etc., they will have exponentially smaller coefficients compared to psi naught. So this is why it can get to the exact ground state without making any other assumptions than your initial state has some overlap with the exact ground state. Pictorially, this just means we start from some energy distribution, and then as the time goes, I'm going to be left with only exact ground state if you were to just enumerate the bit strings and look at the overlaps, exponentially decaying, and you will eventually get just psi naught.
But there's also an exponential number of states, right? So this is overly simplistic, obviously.
You mean the pictorial representation is?
No. You said that you need some overlap with the initial state. No, I mean, there's an the overlap will be exponentially small. So
that is okay.
I mean, That's
In the
also-
limit of tau going to infinity, it doesn't matter how small initial overlap was, you will always get to, well, assuming the
There's a
gap
combinatorial
is not
factor,
zero.
no? I mean, the question is how does it scale with the number of particles, right? You had the scaling with exponential n versus polynomial n. And certainly if I think of a condensed matter system, there's a density of states which grows exponentially. And so for any finite t, if you don't scale it with n massively, you will lie somewhere at a finite energy, right?
The propagation time is set by the gap in this. Are you saying your gap is?
Okay, so what I'm saying, basically, you go to the gap. I mean, let's assume a very simplistic system, independent excitations, right? So there's 1 choose n states at energy 1, 2 choose n at energy 2, 3 choose n at energy 3. So you have an exponential growth of a number of states. So if you have the same overlap with them, your overlap with a certain energy grows exponentially. So you have to fight this to suppress it, right? So it's not just, I mean, each state is suppressed exponentially, but there's exponentially many of these states.
I think it's a big issue in condensed matter physics, but it's
But I mean,
Not
if the
so much
motivation
in
is a scaling in
quantum
n, that's important. No? I mean, if you look at a fixed problem size, this whole
I
scaling
mean, it doesn't
thing is
matter how
important.
many states are hidden in this ... because all these other terms will carry exponentially decaying term.
But there's exponentially many of them. It's like saying 0 times infinity is 0. That's a bit arbitrary. No?
the KCF wave function has a good overlap.
No, if there's a good overlap, that's a different thing.
Well, but the energy
Doesn't
will
matter.
be weighted by E naught times 1 plus E naught times squared coefficient. So you're talking about squaring exponentially decaying terms. So you're going to get very, very tiny signals from
The
them.
overlap
I
of the
think-
gap, that's all. You have the energy gap and the overlap. That's all.
Can I make a comment here? Right, that is actually just spectral theory. The problem is, can you send tau to infinity? Right? If you want to do it approximately, then this objection applies. But at the moment, you told us send tau to infinity. If I do that, I'm good, right?
Yep.
So far, we have to accept that. What he does
Yeah, no, if you
later,
can send tau to
that's a
infinity, sure.
discussion we should probably have later, because he cannot send tau to infinity anyway. So.
Yeah. But in practice, this decays pretty quickly for the systems we looked at. As long as ergodicity holds, it has to decay very quickly. So the power method I just explained, you can't really do it as I explained because it would scale exponentially with the system size. So that's where AFQMC comes in. We want to implement this power method in a stochastic way. So this is stochastic realization of imaginary time evolution. The goal is I don't want to have any obvious exponential scaling coming from the fact that we have to store the state vectors or represent the propagators in the exponentially growing Hilbert space. So I don't want to do any of that. That's the goal. So we're going to discretize the time. So limit of tau going to infinity is now converted into limit of taking time steps to the infinity. So I have a discrete infinitesimal propagator in imaginary time, e to the minus delta tau h. Delta tau is very, very small number. Depending on the application, you can use large number. We typically use 0.005. That seems to work for any systems we've looked at in chemistry and material science so far. We do use trotterization, which is just breaking up this H1 and H2 from e to the minus delta tau h. And this error we have is not usually an issue because the statistical error we have is usually greater than delta tau square, especially with this tau value I said we use, which is 0.005. We do actually have to rearrange this term to write it in terms of sum of squares. So I'm not going to present the math details of this, but just trust me on this. So you can rearrange this term first by swapping these two operators to have A dagger A, and then you can decompose these two electron integrals with Cholesky factorization to rearrange everything into sum of squares. So when you do sum of squares, you can do something quite neat. So I just rewrote the infinitesimal propagator one-body and two-body term. And I'm going to do this Gaussian integral. So I'm going to go backward, where I know what's on the left is going to be the same as what's on the right if you actually integrate out the x variable. And this x is what I will call auxiliary field, and that's the origin of this name, auxiliary field quantum Monte Carlo. So we take this two-body Hamiltonian, which I know it's sum of squares, so that's essentially my alpha square, and I can introduce this auxiliary field variable x, which will be coupled to this. I forgot to mention that V alpha here is a one-body operator. So now I took the two-body term, which is V square, and then on the right, I only have integration over auxiliary field, where the fields are coupled linearly to one-body operator V. Okay? And we do have what we call Dulles theorem. What it means is if I start from a Slater determinant, and I have a set of one-body operator applying to it, and then these one-body operators are all exponentiated, Dulles theorem says it's going to map the resulting state after you act these one-body propagators will be another Slater determinant. So, yes?
Okay, one question. In this Hubbard-Stratonovich transformation, that's where you introduce this new field, right? This Hubbard-Stratonovich field work. Then depending on the interaction, whether it's attractive or repulsive, you have to choose, if I remember correctly, a real or imaginary field. Does that change anything later if you can still do it?
No, it doesn't change. The theory works regardless of whether it's repulsive or attractive. Attractive ones are actually even easier for us because it's going to be sign-free. Oh yeah, quantum chemistry Hamiltonian is repulsive. So yeah, it's not sign-free, unfortunately. We're going to get to that point soon. Any other? Yep.
Is X auxiliary field like fermionic or is just general?
They are just scalar fields, so yeah, just numbers. Any other questions? So you stitch everything together into this, applying this infinitesimal propagator over and over and over again. You quickly realize there is a high dimensional integral to do. If you had only one integral, maybe you could brute force it, but it's going to, the number of variables you have to integrate will scale exponentially with the number of time steps you take. So this is where Monte Carlo comes in. We want to sample this high dimensional quadrature problem via some Monte Carlo sampling. Good news is we removed the exponential overhead. As I said, applying this one-body propagator to a Slater determinant will give you another Slater determinant, which is very efficient to store, and one-body rotation is also very efficient to do, just cubic scaling on the classical computer. So we remove all the exponential overhead. It sounds like a great method. And we do have a way to compute energy, local energy we call, efficiently. So what's written as EI here, we call this local energy. We do have an efficient way to compute this. I'm not going to write out all the equations, assuming psi t does not complicate that computation. We do have an efficient way to compute EI, and therefore we can actually compute energy as a function of imaginary time, and we are interested in infinite imaginary time answer eventually.
So, sorry, can you explain again where the exponential overhead went? I mean, I can see you can absorb part of the Gaussian integral into the Gaussian state.
So I'm saying...
And there's a non-Gaussian part, right? And you iterate this. So where's this going?
Non-Gaussian part. Which is the non... Are you calling this non-Gaussian?
I don't know. I mean, something should be non-Gaussian in the end, no?
Something is non-Gaussian if you carry out the quadrature exactly, analytically. So we had two-body term. We're using this Hubbard-Stratonovich transform to write it as one-body term on the exponent coupled to auxiliary field x. So this v hat x is just a one-body term that depends on the field. And then I also have one body Hamiltonian. So overall, everything is one body, but you do have this quadrature to do.
So it couples to x, and that kind of encodes the.
Yeah, that encodes the fluctuation.
So you sample over this x integral in infinitely many copies, or finitely, hopefully.
Yes, that's the essence of the method. So per sample cost, everything is cubic scaling, which is too good to be true. So you are sort of expecting to see sign problem if you're here in quantum Monte Carlo. We do have a problem that is actually worse than sign. We do have a phase problem. I didn't emphasize enough, but in here we have this I here that makes these determinant orbitals actually complex valued. So I'm going to get to the point where the phase problem happens. So as I said, this is really too good to be true. We do have a phase problem. What it does to us in the end is that we ambitiously launch this AFQMC calculation, as I explained. For some system you wanna compute the ground state for. If we had done exact imaginary time propagation, it will exponentially approach the E ground here. But if you do AFQMC, initially it sort of goes with this exact imaginary time propagation, but at some point it becomes too noisy to be any meaningful. So your signal to noise ratio will eventually blow up. You're essentially collecting random number at some tau value. And this can be actually seen by looking at this statistical average value I mentioned. It turns out this weight sum over all these weights, is decaying exponentially with the system size. And this is due to the fact that these weights are complex valued, and then they are not restricted to any specific quadrant. So they can freely rotate in 360 degrees in the complex plane, where on average, you're going to get a tiny number. So knowing that this sum will decay exponentially with n, it's not hard to actually work this out, where this variance has to grow exponentially with the system size. So to compute fixed variance, you need to increase the number of Monte Carlo samples exponentially to beat this exponential growth in the signal to noise ratio. And this is where the exponential overhead is coming from. Per sample, where cubic scaling, it's great, but we need exponentially many statistical samples to get any meaningful results in the end. So we want weights to be uniformly signed. So this is where the first approximation, and perhaps the only approximation in this talk, is coming. So we do have an importance function. So we actually use some a priori chosen trial wave function to update the weights. So this comes from the distribution that is actually whatever that overlaps more with psi t will be sampled more. This is our importance function. And this is actually also complex valued. So what we do in phases approximation is we're going to take just the absolute value of this importance function, and we're going to even add maximum between 0 and cosine theta I. So cosine is the argument of this overlap ratio. So from tau to next time step, I'm going to compute this overlap ratio with a priori chosen wave function, and I'm going to throw away the complex value part, and I'm going to take just the absolute value. And if this value this is actually called cosine projection, because we take this value in complex plane and we just read off the real value of it. But if that real value is actually negative, we're going to throw away that sample by zeroing out this weight. Seems very ad hoc and hacky, but it seems to work well for the problems we've looked at so far. Many problems we've looked at so far.
Does this introduce a bias or not?
It does introduce bias, yes, exactly. But good news is we don't have exponentially growing variance anymore. So we have overall polynomial scaling, including the sample complexity, but we don't actually get exact answers anymore. Okay? So this is a biased AFQMC algorithm. The result is no longer exact, but as I said, it's overall efficient. You have to pick this good trial wave function that sets the boundary condition for your imaginary time propagation. If you pick a bad trial, you may actually get even lower energy than the exact ground state. It's not necessarily...
How does that happen?
Why is it non-variational? Is that the
Yes,
question?
that's the question.
Um,
Sounds puzzling, no? Because you do an imaginary time evolution. I mean, as long as you think about doing an imaginary time evolution on a state, it's still a state. So it's variational, right?
This comes from the fact that we do not evaluate the energy with the variational formula. So we have a left and right state that's different. It's not guaranteed to be variational, unfortunately. And the non-variationality part comes from the phases approximation. If we did it exactly, it is exact. Exact and of course variational. The approximation here is like this would have been the exact. You need to weight this by the magnitude and have exponential of I theta. So that would have been exact importance sampling, and then that doesn't get rid of the phase problem. The approximation we make is we take this importance function, we take only the magnitude, absolute value, and then we're going to take only the real axis projection of it, but if it's negative after the projection, we're going to remove it. So that's the, yes?
So does, so are you saying that if your trial wave function has the correct nodal structure, then you don't have any error from your projection and it's unbiased?
That is correct. Yep.
So that's what determines a good trial wave function, not necessarily the state itself, but if it has good nodal structure.
Yeah, nodal in this sense, yeah. It's not a real space method, but yeah.
No, yeah,
Yeah,
sign.
yeah, exactly. Yep.
So in that formula, before you make this phaseless approximation, the expectation value, numerator and denominator, as exact formula, they are real values, right? Separated.
This and this?
No, up there.
This and this?
Yeah.
No,
No?
they're all complex value.
But the ratio is just real.
Ratio is by construction real because we're going to take only the real value of it. So on...
I'm asking as an exact formula.
Sorry?
As an exact formula. I mean,
As an exact formula, it is not guaranteed to be... So on average, it has to be real value. That's why we actually throw away numerically the imaginary part.
okay.
Yeah.
Okay.
Yeah. I did check it at some point myself.
Is there any way to see when this approximation kind of performs badly? Because, you know, I mean, doing approximations is fine if a red light turns on if you're doing badly, but if you just get some energy, you don't even know if it's variation or so. It's getting hard to benchmark it, I would guess.
A great question. That's, I think, because quantum chemists don't ask that question. I think that's why AFQMC has been more popular in my field than in physics.
But why don't they ask it? They just use it.
Because we are used to couple cluster theory, which is not guaranteed to be variational either. And it is the gold standard.
You just have the choice between different uncontrolled methods.
Exactly.
But don't you get some estimate? Don't you get some indication of error whenever you start projecting out? When you start deleting a lot of negative signs? I mean, can you plot the errors, the values as a function of like some net
I see.
discarded weight, and then does that make sense? Or?
Yeah, if all of a sudden so many walkers are dying, there is a problem in your calculation. Yeah, either you're using too big time step, or your trial by accident you use like wrong trial. If it's actually all correct, like there is no bug, I don't think walkers should die so quickly. But you do see growing variance in your estimate. So we do have what we call zero variance principle. So as your psi t gets closer and closer to the one of the eigenstates of H, our statistical estimate of this will have a smaller and smaller variance. Become 0 if you use exact eigenstate. So we do see some symptoms of your chosen site trial failing, but we don't really have a way to quantify it for real applications. Does that make sense?
So when you delete these negative signs that show up,
Yeah.
they're deleted and gone. You can't use them for any kind of estimate.
We haven't done that yet. That's an interesting research direction I thought about, getting some perturbation theory estimates to correct this bias, but I haven't been able to make much progress. Because the approximation here is ad hoc by nature, it's very difficult to improve beyond this, actually. Yes?
If you do go below the ground state energy, the variance wouldn't be 0, right? Or
Oh, the variance here, I don't mean like h square minus expectation of h square. It's literally the variance of the trajectory I have when it plateaus.
would you be able to track the variance of the Hamiltonian?
Like the actual wave
actual
function
H squared.
variance, you could compute it. Yeah, you could.
Is the phase list approximation only within the quantum chemistry community, or is like Xue, like when Xue used it for Fermi-Hubbard model, did he also use phase list approximation?
He uses what we call constraint path. So if there is only like Hubbard type n, like density product, diagonal densities, you can do what we call discrete Hubbard-Stranorovich transform. So there you don't actually get phase problem, you get just the sign problem, and that's the original BSS QMC. And then we apply constraint path approximation, which is exactly the same as phaseless in that context. Any other questions?
So when you go back in the Hubbard-Stranorovich trait, the sign in front of the phase part, that's arbitrary, right? You can choose.
That's correct. Yep,
So it's
plus
a complex
minus.
conjugate.
It doesn't matter. Yeah.
Yeah.
Yep.
So does that mean that it's a complex phase? It's just in a conjugate. I mean, either direction is equally probable. Understand?
That is correct. In fact, this Gaussian integral, yeah, that is correct. But that doesn't really help us much in the end, because, yeah, I mean, the question is whether it actually goes to the negative direction at all. Like if everything is strictly contained in this quadrant, maybe cosine projection would have worked better. But yeah, I mean, the fact that we are making approximation at all is really, yeah, what gets us in the end.
Can I ask a question?
Okay.
The alphas in the formula are self-adjoint or not self-adjoint? The V alpha hat.
Self-adjoint, yeah.
Because then you can replace x by minus x and you...
That's correct. You would be able to cancel all of the odd power terms, but they are gone because it's actually Gaussian quadrature. Yeah, I thought about that trick. I was disappointed in the end. It's okay. Great question.
I don't know how to implement in a Monte Carlo, but as an energy formula, somebody also has this question. If this, it's integrating over x variable, auxiliary variables.
Yeah.
You can always set a point approximation. I mean, they're going into complex plane.
Yeah.
And that will mitigate this sign problem, the phase problem that you're referring to. Is there any way you can implement that in the Monte Carlo?
We do have what you are saying. It's called force bias. We will get to what force bias means in few slides, but the fact that it reduces the phase problem involves making saddle point approximation, which I will not cover today. But yeah, we have a dynamical shift that we compute at every sample, every time step, that basically shifts the distribution of the Gaussian that we're sampling, that is meant to design to reduce the phase problem in the end. That's called force bias.
One more question. Did you try analytic continuation?
to go from imaginary time to
How? Sounds weird, but often that's the only thing I can do.
I think dynamic. So, are you suggesting that I take real-time propagation estimators and analytically continue to imaginary time?
That's exactly what I'm suggesting.
I
Because
yeah.
sometimes you have these resolvent formulas and these contour integrals, and if I don't know what to do, I have to resort to contour integrals. It's not so nice, but sometimes it's the only thing you can do.
I see.
Well, usually real-time evolution is harder than imaginary time evolution.
You
I
will
know, but
The
he has this cancellation problem.
you will
right?
get dynamical phase problem too. It's gonna be harder, I think. Where was I? Oh, okay. Now we're here. So I wanted to say the quality of trial really determines the accuracy of AFQMC. So I advertise this accuracy and cost of AFQMC. That is with the simplest possible trial wave function mean field, Hartree-Fock. So the point of AFQMC research nowadays is really to pull this point upward without actually shifting it to the right. That's been extremely hard.
What does good trial mean? Does it mean high overlap with the state you need, or is it a more fuzzy thing? Because you could imagine that maybe you start with something with a bad overlap, yet it doesn't give many terms you have to drop, right?
Yeah.
That's what you really care, like nodal structure.
Good trial in this case really means the trial that gives you the best energy.
That's not very useful somehow.
That is not very useful. We don't really understand so well where the phaseless approximation fails. The only thing we've done so far is to run as many calculations as possible, like we did for couple cluster theory, and make sure that there is no surprise. There hasn't been any
empirical understanding.
Empirical this whole plot here, except the x-axis, the y-axis is completely empirical. Yeah.
But in some sense, having the right nodal structure is the thing you want, but that's nothing you can easily tell.
Yeah. So I don't know. I have 13 minutes left, or how much time do I have left?
Yeah, basically.
Okay.
That includes questions.
Okay.
So 3 plus 10.
Okay.
You can mix the questions in with your.
Okay. This is the actual research part that I wanted to tell you today. So the first is selected CI wave function. We sort of heard about this from Nick's lecture before. So this scales exponentially because the number of determinants, so these are linear combination of different determinants. The number of determinants you need will scale exponentially with the size of active space. So it is guaranteed to scale exponential with the number of orbitals in your active space. I was hoping to cover this. I'm not sure if I'll have enough time. So we do have an ongoing work where we are using matrix product state, which we also heard from previous lectures, where we're going to factorize this into occupation string determinant sum into matrix product state form. This also has a exponential scaling, not because the bond dimension scales exponentially, but any finite bond dimension you like, you give me that. It will scale exponentially to compute the necessary overlap if you have an MPS form, which is unfortunate, but it's exponential scaling due to different reasons from the above.
So if I have MPS and want to do imaginary time evolution, what I would do is to then truncate the bond dimension again and stay within the MPS manifold. So why would you want to take MPS and then put some diffusion or auxiliary field or whatever Monte Carlo on top? Rather than doing the imaginary time evolution in the MPS manifold and truncating.
So what we were going after was to handle strong correlation with MPS within the active space. What you're proposing to do wouldn't work for weak correlation, where I have 2,000 orbitals. You're not going to run imaginary time evolution of MPS for 2,000 orbitals. Yeah, but you could consider doing AFQMC for sure. We've done this. The question is, can we handle what's actually contained in active space, the strong correlation? So our initial thought was we would use this for a strong correlation within the active space, and we're going to do weak correlation with QMC. The only requirement is to be able to compute this overlap value, which we can. I also use quantum circuit. This has a different reason to exponential scaling. It also scales exponentially with the number of orbitals in the active space. So we have three great options that all scale exponentially with the number of degrees of freedom in your active space.
So, sorry, where's the exponential scaling in matrix product states if you do the AFQMC on top?
So this one is actually coming from the fact that phi here is arbitrary Slater determinant. It's not computational basis. Yeah. So it's like doing free fermion simulation with MPN. Yeah, exactly. And this one has a different reason to exponential scaling. It's due to the fact that this value can be computed from the quantum computer up to an additive error epsilon. And this very value decays exponentially with the system size, exponentially to 0. So that epsilon needs to be exponentially precise with the growing system size. So all three approaches I thought about all scale exponentially with the system size, but they do still have some use cases because we're mainly interested in adding weak correlation on top. So this is a detail of implementing new trial. You only need to worry about overlap evaluation. The left one, this is the force bias, which is a dynamical shift to ameliorate the phase problem. This is the local energy you would need to compute the global energy estimate. We proposed a scheme, little embarrassing to look at in the sense that this is probably the simplest one could actually write down without having to worry about any exponential overhead. What we did was, well, this is a one-body operator, so we're going to insert resolution of the identity here, all possible single excitations from phi. We're going to do the same for Hamiltonian, all possible doubles. So this one naturally gives this scaling. The problem of this polynomial overhead is the fact that it's multiplied to the cost of overlap. Although it's polynomial scaling, this makes classical calculation impossible to do with any trial wave functions I mentioned. So that's the part that I try to get rid of. This is done by thinking about how to get these estimates by taking differentiation of the overlap. So the first one, force bias, actually comes from differentiating this overlap function. So here on the exponent, I have some one-body operator, right? There is only AP dagger AQ. I know for any values of theta how to rotate this phi into another Slater determinant by tilde of theta. And then I'm going to compute that overlap, but then differentiating it with respect to theta at theta equals 0 gets me what I wanted, which is the force bias. Okay, so what happens after we do that is that the cost of overlap, which used to be multiplied to the system size order n square, that can be completely removed, and we can actually have n cubed cubic cost plus some overlap evaluation cost, C of overlap. Local energy, which you could have probably guessed what I would do, I made a typo here. There should have been AP dagger AQ, AP dagger AQ here. So I have two rotations to do. But what I'm going to do is I'm going to take second order differentiation, one with theta, one with kappa. It's a diagonal element of that Hessian. And then if I set all the other values to 0, theta and kappa, I'm going to get the two-body estimators. What happens once you recognize this and do it is that the cost of evaluating local energy, which used to be n to the 4th times the cost of overlap, is only linear in n times the cost of overlap. So this really makes what used to be impossible to do possible with this trick. So let me show you selected CI. I probably can skip all those. We had some algorithmic improvements to make the cost of evaluating the overlap to be n determinant plus n cubed. So if you have a list of determinants, you would think that I should have a scaling that goes with n determinant times n cubed, where n cubed is the cost of computing overlap between two Slater determinants. So we've decoupled that. That would be the naive algorithm, but we've improved it all the way down to this. There is an interesting example we've done, which is called torture track. There are two conformations of the Cu2O22 plus that people studied. It is biologically relevant because you can find enzymes containing this at the core active site. It's called torture track because no method was working before AFQMC. You can sort of see, I took this from someone else's paper, but you can sort of see the energy variation between different methods, some multi-reference couple cluster methods and CASPT2. It's on the order of 60 kcal per mole. So we are aiming to get 1 kcal per mole, so this is really, really alarming. So we really nailed this. I think we went up to 52 electrons, 290 orbitals to provide exact answer in the basis element. This is the first time for this specific bimetallic complex. Nobody could actually do this. I want to emphasize this is not just tiny active space strong correlation. This is including both strong and weak correlation. And how do we know if it's exact? Well, we did some unbiased QMC calculation where we removed the phases approximation. We checked it for smaller basis set and smaller space. So we do feel pretty confident that this has to be actually exact. Within the error will be less than a kcal per mole. And this is only possible with the algorithmic development that I explained. So this QMC PEG is the software that I like a lot, but it implements the algorithm that is not naive, but a little better than naive, but the previous state of the art. We actually improved at least 2 orders of magnitude that actually made this convergence possible. We have 1 million determinants in QMC trial.
You're going to keep track of the error sources, and then whether it's coming from intrinsic approximation error or the systematic errors.
It is the intrinsic approximation error. We do converge every systematic error we can think of. So the only error we think we have is the error from approximate trial. Yeah. Should I finish it here?
Go to summary.
Okay, I will go to the let's see. Okay, oops. Okay. I hope that I convinced you that AFQMC has some flexibility that other methods don't. You don't really get to choose trial wave functions for couple cluster theory, for instance. It's not very easy to implement them. I do want to have a polynomial scaling improvement to Hartree-Fock, something that doesn't scale exponentially, but this seems very hard. I haven't had a good success. I didn't get to this part, but I think there might be an opportunity for demonstrating quantum computational advantage of computing wave function overlap. But it needs to have very specific setups because your overlap can't decay exponentially too quickly for quantum computers to compute very well. With that, I will, this is my acknowledgement. I would like to mention that AFQMC code is open source and it's in IPAM. QChem is the code that I use to generate some of these trial wave functions. Not open source, you would have to buy the license to use QChem. And thank you all for your attention.